Hello everyone. In this video we're going to be discussing the linked list implementation for the union find data structure. Up on the screen there we have two sets. They are disjoint. The first one has elements x1 through x5 and the next one has elements x6 through x8. The disjoint sets we are represented by linked lists. There's nothing fancy about that. We have two different linked lists. The angular arrows there represent the pointers to the heads of the linked lists. And then this is a doubly linked list, so we have both forward links and backwards links. That's not necessary for the data structure, but it does give you some free efficiency in some algorithms you may want to write involving the data structure, so we'll use that. A lot of the operations on here would be rather easy. To determine if two things are in the same set, you could just loop through and find the head of the pointers and determine if, the head of the linked list and determine if they're the same. So that's not too bad. To determine to determine a representative, you could again use the head of the linked list. And to make the set, you just need to assign a bunch of pointers to the right places. The one thing that's a bit annoying though is that to find the head of this linked list, you might need to iterate over the entire linked list. One way to get around this is to have every single element of the linked list have a pointer to the head. So what I'm going to do is modify every element to have a head pointer that points all the way back to the head of the linked list. So we have a bunch of these arrows all converging towards the head. So each one will have a head pointer. And another efficiency we're going to get is actually, if I wanted to combine these linked lists, let's say I wanted to perform the union operation with the set that has x1 in it and the set that has x7 in it. I want to make them a single linked list. There are several ways we could do this. Probably the most intelligent way would be to just take the end of one of the linked lists and point it towards the start of the next linked list. So maybe the most efficient way to do this would be to take x5, point it at x6, and take x6 and point it back at x5. Seems just as good a solution as any. But with the way this is written, it's not necessarily obvious how you get to x5 efficiently. As we have it, if I needed to find out what is the end of my list, the tail, I would have to iterate over the entire list. So we're also going to add in a pointer that points to the tail of the linked list. And we have all of these pointers up top that point to the head. Same thing down below. This should have a tail pointer. And all of these should have, head pointers. Let's point to the right thing. That should point back to its head. That should point back to its head, and that should point back to its head. And on top of doing the rearranging with the red lines there, I would also need to adjust all of the orange lines on the bottom linked list to point up to x1 instead. But outside of all that kind of tedious pointer manipulation, that is the extent of what we need to do. For anyone taking the system series, you will have implemented things similar to this several times, and you'll know it might be tedious to debug and troubleshoot and guarantee you get this correctly when you code it, but it's just a bunch of pointer rearranging. So, with that in mind, let's see what the code looks like. We have all of it down here. Some of these methods are really easy. Ignore the union method for now. So, if I can do this correctly. Undo. See if I can block this off. Nope. We're not going to do that then. So let's look at the make set method. That's just creating a linked list with one element. We initialize the head to be the thing. We initialize the tail to be the thing. And the next element is null. There's nothing after the head of the linked list. So this make set operation here, what it does is it creates x. It points to itself and says that's the head. It points to itself and says that's the tail. And it points off till null over here. So this is the head pointer. That's the tail pointer. And that's what we have. Seems a decent start. To find a representative for the set, the find set operation, we just return the head. Nice and easy. So that's not too bad. The union, what we're going to do is find the head of both linked lists. So we find the heads of both linked lists. And then we're going to take the first thing we're trying to union. In this case, we called that X. We're going to find its tail. So in our example above, we find x1 by following the head pointer. We then take that and then go and find the tail and set the thing that comes after the tail, the next pointer, to point at the head of the second linked list. So the thing that comes after the tail of the first linked list is the head of the second linked list. Seems reasonable. And then all that's left to do is update the head pointers for every single thing in the secondary linked list. So we're going to start at the head of the second linked list and update all of the head pointers. Update head pointers. And then after that, we just need to make sure that we assign the tail correctly, which is that the first linked list's tail is now the end of the second linked list. So we update the head of x prime, which was the head of the first linked list, to be, sorry, the tail, we update the tail of x prime to be the tail of y prime. X prime here corresponds to the first linked list's head, and y prime to the second linked list's head. There's a lot of pointer rearranging here, but it's not too bad. How long does this code take? A bunch of this code's easy. Make set, that's going to be theta of 1. Find set, that's going to be theta of 1, just pointer rearranging. And union is going to be theta of the size of linked list with y. And that might be a rather dumb way of doing it. It could be the case that y is a gigantic linked list and x is a linked list that has only one element. So why would we do this in a very inefficient way? Let's see an example of that. I have one linked list here. It has one element. And then I have some other linked list over here that I'm unioning together with it. So let's draw our arrows for our linked list. And as the code is written, each of these also has a head pointer. That points back, and a tail pointer that points there from the head. And now, with the way we have it implemented currently, if this was my set x up top, and the one below was my set y, what I'm going to do is actually iterate over that very long linked list, despite the fact that I don't have to. I could instead be intelligent about what I do and assign x to be the new tail of y. Look at the smaller of the two and only iterate over that one. So a reasonable modification of this would be to take the exact same code and simply determine which one of x or y is in a smaller linked list, and then that is the one that we're going to adjust the headers of. That way we can minimize the runtime of that while loop. So I'll write that in some more complicated words. We could improve this runtime to be theta of the minimum of the length of x and the length of y. Which in certain applications might be a major gain for your algorithm. But here, we don't really need to analyze it too much. That's all we need to see with this implementation. A lot of pointer rearranging, and the runtime here is proportional to the length of the linked list. That may or may not be efficient, and there may be better ways to do it. We will also be analyzing a tree implementation of this data structure, and we will see that we can gain some efficiencies in that way. It sometimes might not make sense to iterate over an entire linked list in this manner, because we only care about certain parts of the linked list, and the tree will give us some of that extra efficiency. That's all we really need to talk about for the union find data structure with linked lists. If you want, you could look at the files on Carmen and view an implementation of the second version called a weighted union, which is very similar to the code we have done here.